Okay, welcome back to this last part of this fourth episode, which I believe will be the last one for this time. I have done a little bit of optimizations and tidying of the code since the last time. And I've also made it a little bit more interesting to see. So actually I've made a cube now that is moving, and it's just animated, so it's not full 3D calculations and these things, but I'll show you how that is done. And it's, you know, some things that I might do in the future. However, my time is going to be a bit limited going forward now. Suddenly there's a lot of things to do, and suddenly there's not so much things to do. So right now I'm entering a period for this year. It's going to be a lot of things to do, so there will be less time for these things. But that's also why I wanted to round this off now. So I have a circle routine which is done. That I might want to add just to draw circles on the screen as well. Software sprites, meaning text or objects that you just plot out. And some kind of handler to deal with this, and of course some benchmark tools, which leads us to the optimization. It's too many to count. Never-ending story. If you want this to be as fast as possible, you need to use charset mode, but that's outside of this scope, so that may be for some other time. As of now, I don't think there's any bugs, but you never know. So let's go through the code. I promised you a full explanation of it. So this part here, that just basically creates the sys statement in BASIC, so it automatically runs the code when you start it. And then here we have D018, which controls the charset or bitmap location and screen memory location inside a VIC bank. The VIC, the video chip, can only access 16 kilobytes, and there's 64 K of memory, as you know. And then you control with this DD00 which of these 4 banks you are then accessing. So for here, the screen memory one, which is located at 0400, that means that the value of these 4 bits should be like that. 0001. 0000 will then be 000. If this one was 2, this will be 08, etc. And for the bitmap memory at 2000, that is this bit, because a bitmap memory takes half the video bank. So either 0 or 1 on that one. If we add this together, we get this value, which is for the high nibble 1 and for the low nibble 8. These 3 does not matter and would normally be used to select where the character set is, but we're not using characters, we're using bitmap, so never mind, they don't concern us. And that actually means here also I can remove these ones. So bank 0, we write the value 3 to DD00, or bank 1, we write the value 2. Now this gives some advantages when I'm going to flip around the double buffering, because obviously we see here is these 2 bits and that bit are the difference between these 2 values, and between these 2 values is only this bit, so that simplifies things a little later. Okay, here I've made a function dim 0 page with some argument, and then he evaluates or updates 0 page. So this is a variable with whatever argument I pass it, and I return the 0 page value minus the argument. So here I define the 0 page variable, and I set that to memory location 02. You cannot use 01 and 00. Those are connected to the processor's I/O registers or register. So here I create myself a virtual 0 page register, which I want to be 16 bits. large, so I define that to be 2 bytes, and I put the low byte to be equal to whatever value 0 page register 1 is, and for the high byte is +1. And then I do the same for x1, x2, delta x. y1, I only need 1 byte, so that is 8 bits, no problem. Pixel error, I need 2 bytes. Why do I do it like that, and instead of just writing 02 here, and you know, well, this is easier for me. And if I want to move things around or delete, everything updates automatically. I don't need to change. Or if I want to put on offset, I want to put everything up on 80, it's that easy, everything is updated in the entire code. So that's why it's done like that. Yeah, there are some flags and things here, we'll come back to that when we meet them. So main, this is the starting point, which is where this basic sys jumps to. And the first command is a say. Now, this is a bit controversial because there are a lot of opinions about this, and frankly, I don't give a shit. So I do it, and then those who don't want to do it, they can do whatever the hell they want. But in this case, what it does is it inhibits the processor to take any actions to any interrupt requests. Interrupt requests, when you arrive from basic, is if nothing else is happening, that is only from CIA1, timer interrupt. But there are some borderline cases and some issues with it, which may or may not happen. So, and making it fully safe is something that isn't possible as far as I believe. But I think this is as good as it gets. So I stop interrupts, and then the first thing I do, this will stop everything. So no matter what, as long as it's an interrupt request, it will stop everything. If it's an NMI, it's a different story. However, then I check the bit 7 of D011, which basically change between 0 and 1 depending on where on the screen the raster beam is. So as long as it is positive, I will just keep branching until it turns negative. And here, as long as it is negative, it will keep branching. So at this point here, I know it just changed from negative to positive, which means it's at the top of the screen. So this is an easy way to wait for a raster line number 0. You could do like that. This is basically the same thing. However, you must also make sure that let's see, D011 bit number 7 is set before you start wait, because the value 0 happens 2 times for D012, so you have to be sure what the value here is as well. Coming from basic, it shouldn't be a problem, but it's still worth keeping in mind. So here I just turn normal value here is 1B. I set it to 0B here, which basically means that I turn off the screen. Now I'm at the top of the screen and I turn it off. This means that it will not flicker or in the middle of the screen change to another color, so it will happen on the top. So when the raster starts drawing, it is the new, it will be the best transition without fading and stuff like that. Alright, so here I've set the border color to dark gray. I set the screen color to black, which is completely unnecessary because it's bitmap single color, so this color is actually not used at all. But maybe I want to use it for later, so it can stay for now. And here comes the graphics settings. So here 18, as you remember, that was the value here for the screen and bitmap memory 1. So I set that here, and then I also select the bank here. Coming from basic, this should be the default bank, but still I'm doing it. So in case somebody wants to mess around, you will set it right. And now we're still up in the top border, so then when it starts to draw, it will already be set to screen buffer number 1. Then this loop here will fill the screen memory 1 and screen memory 2 with the colors white and black. White here is shifted 4 bits to the left or up, and then it's ORed with black. And these are the 2 colors that control what the color of the background is and the color of the lines is. This loop is a for loop, and using variable I equals 0, so this is the starting value, and as long as I is less than 4, add 1 to I. This means that he will repeat this loop 4 times with the values 0, 1, 2 and 3. When he reaches value 4, he's not gonna do it anymore, then he's finished. And then he stores to screen memory plus 256 multiplied with y. The first value of y is 0, so that's 0. Then the next is 1, and then it's plus 256, 2 plus 512, and lastly 786. And this will basically fill 1024 or 1K of memory. It will be 2K because it's both. You could argue that, well, you don't need 1024 bytes because the screen is 40 by 25, which is actually 1000 bytes. And yes, you can also make a loop that fills only 1000 bytes. It's not going to be faster, but it's going to be more. It will not overwrite anything else. So that can, but maybe I'll do a loop episode one time in the future. Okay, with that done, we will write 7F to the CIA register 1 and 2, DC0D and DD0D. This will stop or turn off all sources of interrupts from the CIA 1 and 2, both NMI and IRQs. And then we read the same values again, which is actually an acknowledge, which means if there was already some active interrupt, which might have happened here, that the CIA1 tried to update the keyboard or something, then you will actually cancel that by this one. Now when all these things are turned off, if we reach this point, if there's no hacky NMI code that would mess all this up, at this point here we just get rid of kernel and basic and have access to full RAM except IO, which we will need. So I will write to this D0 area, that's IO values. Then we call a subroutine which cleans out or wipes out bitmap graphics area 1. So we'll look at that when we get to it. And now I tell him, okay, I want raster interrupted trigger on line 0. And I already set D011 up here, so that's already set, so I don't need to worry about that. And this here will tell the processor where it should jump once he reaches or interrupt is triggered. This one is very clever. Actually, this is something I came up with when I made this series. So it takes the high byte between bitmap memory 2 minus bitmap memory 1. So this one is 4000 and this one is 2000. So that means there will be a difference of hex 20. And he stores this into a 0 page position called graphics bank high. So this is the difference between the two bitmap locations. So this will come in handy later. And then I need a flag for keeping track of double buffering, which I initialize to 0, 0. So I set here, set double buffer flag to 0, which means display buffer number 1 and clean buffer number 2. And I set the value FF to allow buffer swap. That means do not allow the IRQ to swap buffers. The IRQ will handle the buffers in the top of the screen, and he will only be allowed to change the buffer once the code that draws all the lines and clean out all the bitmap and all that stuff is done. Then finally we enable raster interrupts on the VIC, and we acknowledge if there's any pending, because there could be some things happening up here and you already get a trigger, and this may, once you clear interrupt flag here, it can trigger immediately. So I do acknowledge it and I clear it, and from this point, as soon as you reach value 0 on the raster, he will jump to the IRQ location and start to do whatever he does inside the interrupt handler. But when the interrupt handler is not running, we have something that I call a asynchronous code, which starts here. So basically what this does is it starts to clean out the buffer, which is not currently displayed on the screen. And this, you cannot start this prematurely, but we'll see this further down. He tests the double buffer flag, and if it is positive, he jumps to this location. And it is positive because we put it to 0, and 0 is a positive number. So he jumps there and he starts to clean out bitmap 2. That was the reason why I didn't do that up here, because I'll do it down here anyway. If the double buffer flag was negative, he will clean bitmap number 1. So this just alternates depending on the flag which bitmap to clean out. This jump here, this can probably be replaced with a branch if I check what is the exit values of this routine, but for now that doesn't matter. This will save you 1 byte and no time. So it basically doesn't matter. Now, next part here, and this is a bit tricky because all the updates that happens to animations and things like that will be handled inside the IRQ, which will happen once every frame. So you can think about it as you are playing a Doom game or something. This is not going to be a Doom game, but just for reference. All the updates of, let's say, movement and bullets firing or whatever is going on shall update at a certain speed. However, the rendering of the frame that you're looking at depends on the power of your hardware. So then that's when you get this jerky movements and stuttering, or lag as it's called maybe in the professional gaming world. So what we don't want to do is, let's say that this animation has been done, or it's actually, yeah, it's done, and you want to start to use this to render a new frame. However, if I am rendering a new frame and then some new interrupt happens because I couldn't finish before the interrupt started again, this data will be starting to be updated for the next frame. So I somehow need to make sure that I capture 1 frame of data and that it hasn't been changed while I was reading it. So to do that, I have a subroutine which just secure the rendering data, which copies the data from one location to another, and to make sure that it wasn't changed while I was copying it, I have a frame counter which is located on the 0 page, which I just store here. And after I copy, I check the frame counter, and then I just compare it. Well, was it the same value? And if it's not the same value, because the IRQ will update this value, then the data can be corrupted. So then I just go back and I do it again. So this should in theory make sure that you don't get these glitches because you have an update of data while you are rendering it. Yeah, I could use a register here. Let's say I use the Y register and then compare it, CPY it here, but I don't know the secure render data. Maybe this will be more complicated in the future. So, but there's a small optimization possibly here if this one doesn't use both registers, for example. So once that is done, it is secured, we're gonna start to draw it. And then I've defined a macro here, which is called draw line with vertex 1 and a vertex 2. So basically he then, whatever I pass to this macro, the vertex 1 will be written to the x1 value, which is 16-bit, and the vertex 1 y coordinate will be written to y1. And then same for vertex 2, and then he will draw a line between vertex 1 and vertex 2. And then I have just defined where this data is located in our secure data here. Each vertex is 3 bytes, so that's why it's +3, 6, 9, etc. here. And then I just call macros here to select which lines I'm going to draw here. So this part basically is handled with this macro to simplify it a little bit. Otherwise I will have to write this 8 times, I think. Yes, no, it's bloody 12 times, yes, of course. So that will be a lot of code. This macros makes it a little bit easier for me. Once he's finished drawing the lines, he will set a flag, allow buffer swap to 0, which then tells the IRQ that you can go ahead now and change the screen. And then he waits here as long as he just wrote 0 to it, and then the IRQ, once he's done swapping the buffers, he will put this one back to FF. So he will wait here until the IRQ is done swapping the buffer, and then he will jump back to asynchronous, which is back to the top, and then the double buffer flag should be swapped. He should start cleaning out bitmap 1, and then he will start to draw, secure the next animation data and draw the next blah blah blah. So this is the code running in the background that is rendering the frames that we are actually observing. Alright, then every time the IRQ fires, which you remember was at line 0, the first thing we need to do is to take care of the registers, and this is storing the A register and the X register into some 0-page locations. Normally you would store the Y register as well, but for now the Y register, the IRQ doesn't use it, so I don't need to care about it because I'm not touching it. So only the A and the X register. Then I enable bitmap mode here, and I turn the screen back on, so this is going to happen at the top again. And then I set single color graphics mode. And here's the part that handles the buffer swapping. So he tests the allow buffer swap, which was set here by the asynchronous code. And if it's allowed, or if it isn't, he will just jump over this code. If he is allowed to swap the buffer, and remember we're still at the top of the screen, he will flip the D018, and remember these are the 3 bits that we wanted to flip to change from one graphics buffer to the other. And then for the VIC bank there was only 1 bit that we wanted to flip. So this will flip this over, and I don't need to worry about any flags or anything for this. It's just to flip these bits and that's done. But I do want to flip the double buffer flag, so I just flip that fully. And I also flip this value, which if you remember is the graphics bank high, which we set up here, which is the difference between high bit of bitmap memory 1 and 2. And we basically just change that between 20 and 0. And this will, I'll explain this a little later, but it's quite smart, to be honest. And then he turn off the allow buffer swap, and that will be off until the synchronous is done rendering the next frame, and that's it. Here is the part where he will animate the data, and here is where he increases the frame counter. So once he's done with that, he this, you could put this above here, but it doesn't matter. As long as this is running, the asynchronous code will not run anyway. So this will never get interrupted by asynchronous. It's the other way around. So it doesn't matter if you put it here or there or anywhere actually. Then exit the IRQ. These are not necessary because they're already set. So this is maybe if I'm going to add another IRQs later, it's already there. Acknowledge the IRQ, restore the XNA register, and finish. So that's everything that happens inside the IRQ. If I wanted to, for example, add music or something, I would play that inside here. It will be synchronized to the frame update. So as it says here. So everything that should be synchronized to frame update, you do it here. But it's also important to remember, the more stuff you do here, the less time it is outside the IRQ for the rendering to happen. So this is the routine that copies the data. So its secure render data was called from the asynchronous code, and it copies 24 byte from the animated data to the secure data, which is just located here. So this is just copy data, nothing else. And here is the animation of the cube. And it has two types of animations. One is to animate the vertices, and it also applies an offset in X, which means because the screen is wider than it is taller, so we move things from left to right in addition to rotate it. So this handles that, and this one here uses an index, which basically keeps track of which animation frame is being used. And the cube coordinates is then plus the offset is then written to x1 animated. And if it crosses the 256 border, this is handled here. The rotations are 8-bit, but when you move it in X, they might exceed 8-bit. So this is handled there. And cube coordinates to Y, because that's always 8-bit. And then he just repeats that for all the vertices of the cube. Vertex is an edge, by the way, the end points. And then he just updates for next frame. He increases that to 1, so he reads the next data. So this is quite simple. And this is the animated data that he does. And this is what the point. If it's updating this data and then you were drawing it and then suddenly this updates, you would get artifacts and bugs. So that's why we try to secure this data. And now finally the bitmap drawing. And this has changed a little bit, but not that much. Now I've implemented a flag here, which is the x1 greater than x2 flag. The reason for that is that saves me from the 16 bits compares later. I'll show you how that works. Now first of all, we start by calculating the absolute value of delta y. So we take the value y2 and we subtract y1, and if the answer the result is positive, we just copy that or write it to delta y. If it is negative, we take the 2 complement of it, which basically is to invert it from negative to positive. But then also we want to flip the coordinates. So we want x1, y1 to become x2, y2 and vice versa. Why? Well, if we do that, we always know that y2 is larger than y1, which means that we can always start from the bottom and draw upwards. So that is a 100% fact for all lines. At this point, this is alright to do it like that. Maybe later we want to change that. If we start to get really gritty with the optimizations, we might want to make sure that x2 is the highest value, for example. And because that will be faster. So, but that's for way down the line. So at this point we have the final x1 and x2 coordinates, and that they will not change after this point. And we know that this value is higher than that value. Then he will fetch the y2 value and write it to temp y, which is the y coordinate of the first pixel to plot, because we start from the bottom. So we can already do that now, and it's an 8-bit number, so it's done. Then we're going to calculate the absolute value of delta x. Now, I haven't gone through the line drawing theory, and that this is basic Bresenham's line drawing algorithm. I'm pretty sure you can find a million sources on that. Maybe I'll go through it at some later point. However, to calculate delta x, we need to use 16-bit subtraction. So then we load up x2 low value, and we transfer that to the x register. And this x register will be used as the x coordinate low for the first pixel and consequent pixels. So the x register, we lock that into x coordinate at this point. We subtract x1 and we store that to delta x low. And then we do the x2 high, which is stored to temp x, which is the high byte of the first pixel. And we subtract x1 high and store that to delta x high. Now, if this is a positive result, well, that's it. He will go down here. If not, well, he will change this flag, which we set up here, and this will tell us later if x1 is bigger than x2 or not, because that can change. We always know that y2 is bigger, but he can draw in one direction or the other direction. So this actually just sets this flag for us, and then it's easy to test later. At this point we will just take the delta x and invert it. This is how we do that compared to with the 8-bit number. You can do it like this. You can do it like that also, but this is faster, slightly faster. Now, if delta x high, in this case, if it is equal to 0, because delta x high is even if we do this negation here or we don't, the delta x high is the last value we have been fiddling with. If that's equal to 0, well, we don't know if delta x or delta y is bigger. So we need to test that here. But if it is not 1, well, we know that delta x, if it is not 0, we know that delta x is greater than delta y. And it's different ways to handle the lines depending of which delta is bigger. So if dx high equals 1, delta x is bigger than delta y, because there is no high byte on delta y. If it is 0, we have to take delta x low and we compare it with delta y, and then if that is results in a set carry, means that delta x is greater than delta y. And just one thing here. It's just a note, and as I said, for now here, delta x greater than delta y will also handle diagonal lines, and that might not be optimal. So I think this might be better to change this around delta y and compare with delta x, and let delta y branch and carry clear to this one, and let delta y greater than delta x handle the diagonal lines, because I have a suspicion that is faster, but it doesn't matter for now. But that's just a small thing to keep in mind, that you control that here, unless you make a special diagonal line handler, which you can also do. So here we are then. We have reached the point where we are going to deal with steep lines where delta y is a bit larger than delta x. Yeah, as I said earlier, the code here is highly unoptimized, so if you were to do this fast, you should get the X register to hold the pixel error and the Y register to be the loop counter. This will be the fastest way to do this, or the fastest way to use your registers. But this is not done, it's not implemented. And of course, if you want this to be really fast, we could use something called slice code and fractional scaling to handle the pixel error. But that is, as I said, future optimizations. So first of all, we know here that delta y is bigger than delta x, and we have some common setup that is equal regardless of x increase or x decrease. So we take the delta y value and we divide it by 2 and store that to the pixel error. Divided by 2, this will balance the line. And then we need to tell the routines when is it done drawing the line. So then we take the value of y1 and we subtract 1. Because we want it to exit on -1, not on 0. So this means that we don't have to worry about plotting the last pixel and things like that after the line drawing algorithm is done. So we already subtract 1 here, and then it exits and at the correct point. So we take y1, subtract, and then he stores that to some self-modifying code, exit 1 and exit 2. We'll look at that a little bit down. Then we need to figure out, well, is the x going this way or that way? And then now it's very simple to check if it's increasing. I just test this flag that we set up here when we were calculating the delta x. So I already know if it is bigger or smaller. And here I only need to test that flag. So this is a heck of a lot faster than comparing x1 versus x2, which will have to be done in 16 bits. So this is easier. And if it is negative, well, then x2 is greater than x1, means the line will be drawn to the left. So, and here is the routine that handles that. And we preload the y register with temp y, which is the first coordinate to plot. The x register is already set with the low byte of the x. And then we need the temp x. And then it is bit 0, which will tell you if it is more than 256 pixels or not. So I just LSR it, logical shift right it, that will push it out into the carry. And that's it. I can't do that here because I will mess up temp x if I do that here. There's probably a smarter way to do this. So, but for now, this will take care of across the 256 border drawing. And here, usually we used to do a JSR plot a bitmap. I've copied the plotter code into the line drawing routine now. And basically here we set up the bitmap table low, which is the low byte, for the Y position, which is loaded here, which is the pixel to plot. So he fetches that from our table. He writes that to the 0-page register 1 low, which is the 16-bit 0-page register that we define. Then he gets the high byte, and this I thought was very clever. He add carry to this one with the graphics bank high. And this one is either 0 or 20, which means that he will plot this to either graphics buffer 1 or graphics buffer 2, depending on the graphics bank high value. But not only that, the LSR here will also determine if this one is +1 or not. So it will in the same time also handle the above 256 pixel cases, depending on carry from here. So this is 3 cycles inside the plotter to plot to both buffers and the handle 256 borderline. So yes, that one I thought was quite smart. Yes, cheers, thank you. And then we have the set P register 1 and 2. Set P register 1 low and high is then set to the memory location where we want to plot. And then we load the Y register with the bitmap offset, which will handle the X displacement. And then we will also read the bitmask table, which is also determining the pixel in a given byte that we will plot to, and then it will URA and STA it to that location. So it will be the 0-page register, and then the Y here is the X offset. So that's how the plotter works. Now, once we have plotted the first pixel, which is X2, Y2, we need to do some testing here. So what we'll do is we'll get the pixel error, which we set up here, which is half delta Y initially, and we will subtract delta X. Now, obviously delta X, this is a 0-page thing, so of course this should be use self-modifying code here to put this to an immediate value, but this is gonna change anyway, so it doesn't matter for now, but I will save you a cycle in the loop. Now if this doesn't underflow, well, he just stores it back to the pixel error, and that's it. He will decrease the Y value, and then he will take the Y value and check it. Are we done or not? And if we are not done, he will branch back up to loop here. And we already read this is of course also hard, that's why it's better to liberate these registers, and that's of course something that will be happening later. But branches back up to the loop and then start on the next run, and then the Y register is updated with the new value, so then of course the line will be updated as well. However, if this underflows, the pixel error underflows, we will add delta Y to the pixel error, and then we know that we also need to move in the X direction. And this is the only difference between the two routines. So in this case here, it just tests if the X value is 0, and if it is not, well, then you just decrease X with 1. So decrease 1 if you move to the left. If it is 0, well, then you also need to decrease the high byte of the X value, and additionally the low byte. So this is just a 16-bit decrease. So that's it. And then this part does not touch the A register, so what we added carry here can be stored back to the pixel error, and we can keep going until we're done with the loop. So that is the whole routine for handling that line. Here is the same line, except this case it's a 16-bit increase here, and that's it. The rest is exactly the same, but we just increase X instead. So I'm not gonna comment more on that, but it's fairly tight. But of course, blitting. No, we're not blitting. We're plotting. Plotting to a bitmap memory, of course, is a lot more complicated than plotting to a character set memory, because you can line up the memory to be more easy to handle. You cannot do that with bitmap. It's locked in how it is. But there are ways to make this a heck of a lot faster. And of course, these things here, this cost a lot of time. And also, doing the checks like this, we are checking every pixel we plot, we check for an overflow. There are ways, I mentioned it above, we can use some slice code, which means that we can plot like 3 or 4 pixels in one go without checking again, because we know that there's a minimum of 4 that we need to plot, for example. So there are techniques that will speed this up quite a bit. But either way, that is that. And then we're on to the slack lines, where delta x is larger or equal to delta y, which, as I said, then it will also handle the diagonal lines for now, which I'm not really sure is the right way to do it, but or the fastest. Now here, the thing is, we plot every pixel. That is, sorry the expression, stupid. So if you have 4 pixels inside a character that is plotted 4 pixels to the left or right, well, you just want to write that one time and not 4 times, because the writes here, this part is what takes time. It's the worst hog of time in this routine. So obviously this can be handled in a very different way. But for now, as I also said, the idea is not to make it the fastest, the idea was to make it work. So anyway, here again, common setup for increasing and decreasing x. So we divide the delta x with 2 and store it to pixel error. So we get the high byte, divide by 2, store that to pixel error high, and we get the low, and we rotate that right, so any overflow from here is brought in here, and yeah, that's fine. We store that to pixel error low. So here we have a 16-bit pixel error that we have to deal with. The first one, since we right shift, this will always be less than 1 or 0. If it was 0, it will still be 0. If it was 1, it will be shifted out, so it will be 0. But it will be restored. It can be above, so we'll need to take into account this high bit. And then again, here we already have the flag, so we use that to find out which way x is moving. So here we need to exit on different terms. So in this case, the exit is x1 minus 1, and for the other one is plus 1. That depends if we're moving to the left or the right. So here we subtract 1, and we have to check for both high byte and low byte when we exit. So that's handled with this one. And then starts the loop. So here, temp y and high bit is pushed into carry, so this is handled in the same way. The plotting is handled in the same way. And then comes this pixel error stuff, which is of course a lot more grandiose here. And not really sure if it is the best way to do it, but it works for now. So we get the pixel error low. This one of course should be immediate value. Subtract the delta y, and then it's underflow or not. If it is not underflowing, we just write it back to pixel error and we're done. If it underflowed, we will decrease pixel error high, which could be 1. And if the answer is positive, well, there was no underflow, and we can write the low error, and then the pixel error high is just decreased with 1, and we have the new value for low. However, if that underflows, we need to add delta x low, and then use the Y register to handle delta x high, which I then decrease by 1. And this is really weird, but it's how I have to do it. And then depending if the add carry here resulted in a set or clear carry. If it's a set carry, I want to increase Y, because that'll put delta x up to 1 again. This is really strange and a bit hard to wrap your head around, but the Y register then will have the correct value in pixel error high. So you should always decrease it, and then you might want to increase it or not, depending on the addition of dx low. Temp Y has to be decreased because we're always moving. No, sorry, temp Y is easy to decrease, it's 8-bit, so that's it, just a deck. So that's easy to handle, but of course it's this 16-bit stuff here which is a bit more elaborate. But probably if I think about it for a while, we can find better ways to do this. And then we will need to decrease the x position. That happens every time. So this one is transfer x to a. If it is 0, jump to here, and if it is not 0, sorry, skip it. If it's 0, decrease the high bit and decrease the low bit. And then this is the end of line. He checks the low byte, which we already put in where to exit. And if the low byte doesn't match, then just keep going. If the low byte matches, then also check is the high byte correct. So this is the fastest way to handle that. And we don't need to check the high byte every pixel, which you would think would be the normal, check the high first and then low. No, but what's the point of checking the high if the low doesn't match? And yeah, it is faster. So here's the routine for x1 bigger than x2, and it's exactly the same. The only difference here is the part where this is increased instead of decreased. Exit is the same. And that's it. So the plot bitmap routine is not used anymore, but I'm going to keep it in case I'll use it for something else later. And here comes the tables. So this is paged aligned, and this is a bitmap offset table which just adds 8 depending on the index value. So fill 256 values with 8 multiplied with the value of I shifted to the right 3 times. By 3, that means divide it by 8. Bitmap table low. Take the low byte of bitmap memory 1, add 320 multiplied with I divided by 8, and add I ANDed with 7, which will let you get to the individual lines. So that this gives a value between 0 and 7, and then that results in a perfect table for the low byte. For the high byte, you don't need to worry about that, so because that will never change for any 8 values. Bitmask table, yeah, 256 values with the value of 80, and then you shift that value to the right with I ANDed with 7. So 0, 1, 2, 3, 4, 5, 6, 7, which then will give you the 80, 40, 20, 10 bitmask values that you use to actually plot in the pixels. So here is the sinus low and high, and x and sinus y, which basically I don't use these anymore, but I'm gonna keep them for now, but they are not in use anymore since I added this cube thing. This is the X offset data. This is just the signers that will move this cube to the left and right, which I added up here in the animation code. So that's it. Now, clearing out the bitmap screen. This is probably going to be the most complicated part. Shouldn't think so, but there is a lot of theory around this. But either way, in this case, what we have done, we have brute forced just writing 0 to all 8,000 bytes. Why 8,000? 8,000 because it's 40 by 25, which is 1,000, and 8 bytes per character on the screen, so that's 8,000. And there is many ways this can be handled, and I was thinking about this for a while. And you can fully unroll it. You just do LDA 00 and you store it to 2000, 2001, 2002, 2000 until you stored it to 8,000 bytes. But that's going to take a heck of a lot of memory. So you need 8,000, and it's a store which is 3 bytes each, so 24K then almost to wipe one screen. So that's 48K. So you're starting to get low on memory then when you're double buffering. So it's not viable to do that. And I'm not considering DMA wipes from Reu or Super CPU or whatnot, or any of this block wipe commands. That is not. This is only stock hardware. So on stock hardware, this is how it's gonna be. There's nothing stopping you from detecting exotic hardware and taking advantage of that. Even if it's running on a C128, you can do the 2 MHz tricks in the upper and lower border. It's fully fine to do that, but for now it doesn't take any of that into consideration. It's just how in the heck are we, without blowing all the memory to hell, going to wipe out 16,000 bytes of memory because we have 2 bitmap screens. So first of all, I wanted to make sure that my loops are optimized, and then to figure that out, a branch which goes backwards it can maximum give you 126 bytes from the memory location of the branch OP code. And if you include the dex or inks or whatever you use, then that means n times 3 plus 1 is 126. And 3 is because it's 3 bytes in a star and 1 byte for the dex, which gives us n equal 125 divided by 3, which equals 41.67. 67 means it's 2 bytes surplus. So you could have a CPX or something there. Still manage for the branch to reach without using far branching. This gives us maximum of 41 STAs inside a loop that loops backwards in memory without resorting to long branching. So here's an example with 16 iterations, means that he will loop 16 times. So we will need 8,000 stas, divide that by the number of iterations, which is 16. That means we need 500 STAs. And how many full loops does that give us? 500 STAs divided by 41, which is the max we can have with one. That means 12 loops with 41 stalls. And we need one extra because that's not gonna add 12, doesn't add up to 500. So then we take 500 minus 12 times 41, which leaves us with 8, which is the special case we need to handle in the last loop. So this is one way to split this up. 128 and 256 iterations is special because no matter how we multiply this up, it doesn't match the 8,000 bytes with equal indexing. So they need special consideration for the last loop because they need a lower amount of loops iteration in the last one. And 256 also require special handling. because LDX FF is a negative number, and then you cannot do dex BPL, because if you dex it, it will already be negative. So that's not going to work, so you need to handle that in a different way. Now, we control this by this variable iterations, which then means how many times the loop shall repeat. And then I want this to be a number n to the power of 2. And the reason I want n to the power of 2 is to ensure that this indexing doesn't cross any page boundaries. And this actually makes sure that, and why is that? Well, you get an extra cycle. So if you have store, let's say 20 F, and then you have comma or x equal 15 to take a number. Well, all those 15 stores, every time this loops, will add an extra cycle, so we don't want that. So we want to maintain this power of 2 numbers. And this means that this gives us some few legal iteration values. Iterations 2, loops 2 times, but here we use long branches because it's actually faster. And the same for 4 and 8. 16 uses the maximum loops and no long branches, which is faster. Trust me, I've done the math on this. And then 128 and 256 are special. Fully unrolled, forget it, you can't fit it. So here is the setup for this. Now I'm using 4 iterations, which is this is a compromise then. So the lower this number, the more memory it will take, but the faster it will be. 256 is the slowest. The total stars is 8,000, and then we calculate basically what we said above here, which will give us the figures we need to sort this out. Here I put some assertions because I want to make sure I don't put a wrong number here. And here starts the code. Whew. So 0, 0, that's for sure, we're gonna write 0. If it's 256 iterations, well, x should be 0, 0 as well, and it should be repeated 31 times. Well, it shouldn't be 32. No, 32 you will write too many. So we do 31, and then we will pad it with the last thing. So this is written to the bitmap memory plus iteration multiply with the loop value. And this will produce this regular LDA 0, TXA, state 2000, 2001, 2002, etc. And then we decrease x and we just branch if not equal to 0. We start at 0, so this actually this handles everything, and we don't need any compares. 128 iterations, and as you can see, this starts to get a little bit tricky. So here it's iterations equal 128, and then we start to use our calculations up here to find out how many of these full loops do we need to write. And then it's iteration minus 1, because if you want to write, let's say 16 bytes, you will load x with 15 and decrease until negative, which is 16. And quantity of stars in full loop, then that should also be set to 41, so you could use 41 here. And then this inner loop handles each 41 LDX LDX BPL, and this outer loop, how many of these do we need? Once that is done, we need one last one here, which yeah, I'm not sure if we really do need one here, but anyway. Yes, we do, because 128 is not full, so yeah. And then for both 256 and 128 we want one last one to handle the 3, and it's the same 3F, which is 64, which is then written to 1F00 plus 63 and then decreased until it's filled. That will handle the last part. Then for 64, 32 and 16 is the same as 128, almost. And for 8, 4 and 2 is basically here it uses a long branch instead of splitting it up into 41, 41, 41. And then done. So this allows me to quickly set iterations here from 4 to 2 or 16, depending on how much memory I want to spend on this and how much time I want it to take. And then I have the same for bitmap screen 2. It is exactly the same, only that now it uses bitmap screen 2. And that's it. And then this part is what makes the 3D matrix rotation program from the Kick Assembler manual, which was written by Mats Nilsen. So I just modified it a little bit, but Mats is the one who wrote this in the manual, so I'm not claiming any credit for this. So here it defines a list of vectors, and then this macro will do basically a calculation of some object, which here is a cube, and which then is how long should the animation be and how many times should it rotate around X, Y and Z. That's basically what this does. And yeah, it handles perspective, it scales, it rotates and it moves. So all this is handled there. I fiddled a little bit with the values of the scaling, and also this offset. This is an offset that is applied to get it correct, to fit the screen like I wanted it. And I split this one up just to make it a little bit more readable. And then finally the data is just filled out here. So at this place, cube coordinates, he calls the macro pre-calculate object cube, 256 data for each vertex, and 2 times around X, minus 1 time around Y, and 1 time around Z. So these are the values to make the animation. And that's it. I'm not gonna go into the 3D calculations. That may be for another time, and maybe later I'd like to add this to natively so I can do that calculations inside this program, but that is far up and far ahead. So that is it. Then maybe it's time we take a look at it. So I'm just gonna call it up, and it will look probably horrible. There we go. So here we have our cube, and as you can see, it is stuttery as hell, and this is simply due to processing power. So now is the point where optimizations. I don't think I can optimize the clearing of the screen any more than it is done without resorting to exotic hardware tricks and things like that. So the rotation then happens according to the 3D calculation, and you can see it's moving in X and Y, just so I can make sure it works all over the screen. But can you be sure this will look good if we add more power to it? Well, we can take a look and see. Let's see, I have a super CPU thing here. we go. So now I'm just started the same thing up in the Super CPU emulator, and you can see the difference, I guess. So how do we get from that to that without adding more power? Well, extremely difficult due to the buffer wiping. But the line drawing can definitely be improved a lot. Now, just for the interest of it, of course the Super CPU thing is not written for Super CPU. It doesn't take advantage of anything except increased power of speed in the processor. If you were to write something designated for it, of course it will be very, very fast. But let's just take a look at one last thing. If I can scroll down here. Here, so this is with 4 iterations. Let's take a look at the memory. It's at 64, yeah. The 6400, so you can see here 0, X loaded with 3, which means that he will write 2003, 2, 1 and 0. 4, 8, blah blah blah. Until he reaches 20 FC, and FC plus 3 is FF, so you see there will be no crossing of page boundaries, which means this will take 4 cycles and not 5. That's why the power of 2 things. But you can see everything is in one long list of stores here, and it's relatively fast. You will only have this added 4 times as additional cycles, so it's not bad at all. Now if I change this to, let's say 16, just to show you how that will be done. So it'll be slower now, but there you can see that 16, okay, that's loaded with F. So from 200F and down, and then these are 41 stores, which is the maximum I can do before the branch here will not reach back up again. But you can also see then that the code is definitely a lot shorter than it was before. So that's it. I think let's put it down to 2. Did that reach? Yeah, okay, so now the cube coordinates ends up into the IO space, so I will need to change the memory configuration. I'm not going to bother with that now, but I could do it so that I hide the IO when I read this data. But I'm not going to bother with that. Ah, see, I did it wrong here. So I put 3 iterations, and then error, iteration must be a number of n to the power of 2. Yes, okay, thank you. So 4. Yeah, it pays off with these things. So there you have it, people. I am not gonna spend any more time on this now. I'm considering this complete at this point. And as I said, once real life releases its talents, then maybe I'll get back to this then. But until then, and meanwhile, I hope you all have enjoyed it, and you can also see that yes, it's fully possible to at least do something in 3D or drawing lines, but of course it's slow and unoptimized. But that's it for me this time. Take care and cheers. Bye bye.